So this is Maple. I guess the first thing we should talk a little bit about is how you use Maple to do integrals. We talked about solving ODEs and doing algebra, but it's also able to do integrals. So you use the int command in Maple to do that. So int, you can see right here, takes in two arguments. The first argument is the expression to integrate, and then the second argument is the integration variable. So what this line here says is integrate the expression x squared with respect to x, and of course then that should be x cubed over 3. And the other thing you can do with integrals with the int command is you can put limits on your integrals, right? So if I want to integrate x squared with respect to x between, for example, 0 and 1, so from x equals 0 to x equals 1, you just, with this second argument here, you just follow it by the limits. So equals 0, dot, dot, 1 says go from 0 to 1. And of course, if I do that, then I should get, 1/3 x cubed evaluated at 1 minus 1/3 x cubed evaluated at 0, which is 1/3. So that's how you use the int command. We can use it here to do a couple of things. The first thing we can do is just show that our eigenfunctions are in fact orthogonal, right? So if you remember, for this particular problem, let's see if I can go back to here and actually go into slideshow. So for this particular problem, this was my statement about orthogonality, right? I should be able to multiply any two distinct eigenfunctions together, and if I integrate from 0 to w, I should get 0, right? So we can verify that that's in fact true, and I did that here. So assume I is an integer, assume j is an integer, and then lambda I is this expression here, and lambda j is this expression here. And again, I'm assuming I is an integer, which I need to do in order for this to work, and I am using capital P I, not pi, in order for this to work. So these are two different eigenvalues, right? If I integrate one eigenfunction multiplied by another eigenfunction from 0 to w, you can see that in fact I get 0, right? So that's guaranteed to happen if you did your problem right. You're guaranteed to have these eigenfunctions be orthogonal to one another. In fact, you can prove it. We do that in 764. If you take that class, you can prove that it has to be the case that when you solve the ODE that we solved in order to get our eigenfunctions, and we have homogeneous boundary conditions, any two solutions will be orthogonal to one another. We didn't prove it here, but you can. You don't have to necessarily prove it to yourself every time you do one of these problems. Okay, the last thing that we can use Maple for, which is actually probably the most useful thing, is we can use it to do these two integrals, right? So I can do these integrals, right? I might have to remember with an integral table or something like that, but it's easier just to plug them into Maple. So the two integrals I got to do is I have to integrate sine of lambda I x squared, right? And then I also have to integrate sine of lambda I x, right? So if I do that, sine of lambda I x times sine of lambda I x from 0 to w, sine of lambda I x squared from 0 to w, I get w over 2. So this integral here is just w over 2. And sine of lambda I x from 0 to w is this thing right here, 2w divided by pi times 2I minus 1, right? So that's what this integral here is. So I've evaluated these two integrals. I have now a expression that I can use to solve for c sub I, right? If I solve this for c sub I get that all of my constants are this, and I'm done, right? I have my solution. This is my solution right here. I know how to calculate every constant. I know how to calculate every eigenvalue. So if I plug in an x and a y, I can just start adding up terms for as long as I want to get a solution. And obviously I can't really add up infinite terms, but we'll show in a second you don't need to add up an infinite number of terms in order to get a solution. So let's implement this solution in ease. So yeah, let me find ease here. I think it's right here. So this is the implementation of the solution. I just chose a W and an H and a T sub H, right? So those are kind of arbitrary. And then I choose an X and a Y, so I'm actually here specifying a non-dimensional X and Y. And so these numbers have to go between 0 and 1, and then this is the actual X and Y. And then I implement my solution. So here I'm going to use 11 terms. I calculate for every one of these terms the eigenvalue, right? And I calculate the constant using those equations we just came up with. And then I calculate the terms, right? So this is T sub I is each of the terms, and then just sum them together, and I get my temperature solution, right? So I can now make plots of the temperature distribution. So one thing I did here is make a plot of temperature as a function of X for various values of Y. So just to visualize what this is a little bit more carefully, I probably have to go all the way to the top here. This is temperature as a function of X, right, at different values of Y. So this is the temperature along this line at Y equals 0, along this line at Y equals 0.25 H, 0.5 H, 0.75 H, and then at Y equals H, I'm along this line here, right? So if I look at this, that makes sense, right? I have the temperature always on the left side has to be 0. That's the boundary condition here. They all go to 0. The temperature on the right side needs to be flat. The boundary condition here is flat. And then I just am increasing in temperature as I move up towards up here at Y over H equal 1. These are all with 11 terms, except for up here I did it with a few more terms. You can see they're all pretty smooth actually until I get to this boundary condition here. This boundary condition, I actually need kind of a lot of terms to make it look even kind of reasonable, right? With 11 terms, you can see, there's kind of 11 sinusoids that I'm adding together, and those 11 sinusoids are doing their very best to try to make it look like a step function, which is that boundary condition. But it's only so good that they can do, right? With 21 terms, they can do better. With 101 terms, they can start to do pretty well. But there's always this ringing. And actually, if you think about what we're doing here, we're actually taking the Fourier transform of that boundary condition. So this is just a Fourier transform of a step function that we're using there to represent that boundary condition. We can make a contour plot of the temperature distribution. So all I did here is build a large table. So I'll show you how to do that. Here we'll vary both X bar and Y bar, right? So I'll make a table. I need X bar to go from 0 to 1. I need Y bar to go from 0 to 1. Of course, I can't just, let's just put this in here. So X bar and Y bar, and then we'll look at T, right? Not that, but T. And if you think about having maybe, let's say 20 by 20, a grid of 20 X bars by 20 Y bars, I need 400 runs in here, right? 400. So we'll add those, and then I want to vary X bar from 0 to 1 and Y bar from 0 to 1, but I don't want to go from 0 at run 1 to 1 at run 400, and the same thing here, or all I'm really doing is sort of getting the temperatures along a diagonal that goes across my computational domain. Instead, I want X bar to go from 0 to 1 for the first 20 runs, and then go from 0 to 1 again for the second 20 runs, and so on. So I'll just do alter values, and if you come down here and do repeat pattern every 20 rows, that's what it'll do. It'll go from 0 to 1, and you can see it goes from 0 to 1, and then it starts over again, going from 0 to 1, and so forth. So this is sort of going across my computational domain over and over again, and then I would like these first 20 rows to be at Y equals 0, and the next one to be at Y bar equals a little bit bigger. So I can do that too, right? I go here, and now instead of repeat pattern every 20 rows, I want to apply the pattern every 20 rows, like that. We'll go from 0 to 1, and now you can see all of these are at 0, and then 0.053, and so forth and so on. So now I have a grid actually that goes over my entire computational domain. I can solve this table. Takes a little bit of time, but now I can make a three-dimensional plot. So if I go to plot here and do an XYZ plot and pick, you can pick all kinds of things. This is isometric lines or color bands or gradients or even 3D surfaces. I already built one here so you can look at it. This is a contour plot, right? So you can see up here is 100, or a 3D surface is kind of cool, right? Here's a 3D surface. You can spin it around and look at it and everything. And sure, this is 0, this is 100, and then you can see the boundary condition is flat adiabatic over here, and if I spin it this way, you can see it's adiabatic over there, right? So that's how you do that. The last thing we should talk a little bit about is how you choose how many terms you actually want to use, right? Okay, so if I want to know how many terms I need to look at, what I really want to look at is how quickly the series is converging. So let's look at the solution at a particular location. So this is x and y at 0.5, right? So right in the middle of the computational domain. And if I solve, what you should see is that the series is converging. In other words, the first term in the solution is pretty big, and the second term is much smaller, and the third term and the fourth term and so on. And so the error that you get by stopping at the fifth term, for example, will be no bigger than the magnitude of the fifth term, right? So if I sum all of these other guys together that I am not going to include, they won't be any bigger than the one that I did include. So I know then that stopping after 5 terms, the error, the truncation error, the stopping error would be less than 0.0085 Kelvin, right? And that's how you can judge sort of how many terms you actually need to include in your solution, right? So here I included 11 terms. My error is tiny, right? I'm predicting the temperature to within, what is that, like a microkelvin, less than a microkelvin. Now, the series doesn't always converge this nicely. So, for example, if I were to get a solution up in that upper left-hand corner, so let's go look at that left-hand corner. In the left-hand corner, let's put it back here, I'm at a spot where I have kind of an interesting thing going on, right? Just over here to my left, I have a temperature of 0, and just up here above me, I have a temperature of 100 Kelvin, right? So I'm in a weird spot, actually a physically impossible spot. The heat flux that would be required to actually do this is infinite, right? So if I get up close to this, first of all, we saw that the solution itself is having troubles, right? We go, we'll look at that plot here. Right here at x equals 0 and y equals h, I'm getting this kind of pretty violent ringing. And I can see that again if I look at the series, right? So let's go right up next to that corner, x equals 0.01, y equals 0.99. What you're going to see is this series doesn't converge very well at all, right? I mean, it's not getting smaller. If I want to get an accurate answer, I would need many, many, many terms, right, to get a solution. And so, like I said, there's places where your series can converge quickly. If I was back at 0.5, I would only need, I don't know, let's say 5 terms to get a pretty good solution, a really good solution actually. But as I move towards places where very severe gradients are happening, and actually in this case, physically unrealistic gradients are happening, you're going to find that the series converges much more slowly. All right, so that's separation of variables. I mean, it's not all about separation of variables, but it's enough to go through all of the steps to get you started, and you can get a solution. What we're going to talk about next time mostly is that first step. So in that first step, we said, let's go back here and look at it. In the first step, we said that we have to check that the problem satisfies all the requirements for separation of variables. And almost any problem that you run into won't, not a realistic problem. So there are techniques that you can use to split a problem up into little sub-problems that each can be tackled using separation of variables. And one of them is called superposition. So next time we'll talk about superposition, which is a really important tool that you need to have in order to use this technique for any kind of realistic problem.